We're going to be talking about probability theory now. And probability is the language of uncertainty, as probability is a tool for probability theory is a helpful tool for people to understand uncertain outcomes in the future. Now, I'm not going to teach you to predict the future, but what I am going to do is to help you to understand how randomness and how knowing the set of possible outcomes can help us to determine the certainty with which we're going to see something occurring in the future. This is the basis for hypothesis testing in statistics for psychology. And we want to think about the randomness of outcomes, the randomness of things. The next person that you talk to, what's the probability that that's going to be a male or a female? Well, that depends on who's in your environment, right? If it was just a random environment where you had the whole world in front of you, it would be about a coin toss flip. Looks like it's heads. Heads. See that? So heads is one of two possible outcomes that we have when we use a coin to see what happens. Again, heads. So if I flip this coin again and again and again, you'll see that comes, whoops, there you go, heads. That there's two possible outcomes, right? There's the heads, and then there's the tail. This one is Washington, the evergreen state. All right, so I'm going to flip a coin, and we're going to see what it comes up. Heads. Good, so you keep flipping that coin, and it's heads again. Now keep flipping this coin, and we'll see. Can you see that? Heads. I'm going to keep flipping it. Whoa, there we go. Can you guys see that? Heads. All right. One more flip. Should we do one more? Heads. Now, there's two possible outcomes, heads or tails. You know that there's a tails outcome here too. But when I flip it, it seems like all that's coming up is heads. Why is it only coming up heads? Well, something must be going on here. Heads, 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 heads. What's the probability that you flip a coin and it keeps coming up heads, 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 heads. You can do this as many times as you want. You determine the probability of something by the possible outcomes as the denominator and the outcome we see as the numerator. So each of these times that we do this, we see that there's two possibilities. It could be a heads or a tails. The possibility that it comes up heads is only one of two things. So probability is spoken in terms of decimals. The probability that I would get any one flip of a coin is 0.5. So it's not seemingly so random. Oop, dropped it. Where did it go? Still rolling. Still rolling. Still rolling. Can you see it? Heads. All right. We're back. It's not unlikely for it to show up heads, so you shouldn't be really worried at all that when I flip it, it keeps coming. Really worried at all that when I flip it, it keeps coming up heads. This shouldn't bother you because, well, it happens once every 2 times I do this, right? Why you guys are probably being a little bit annoyed is that you're seeing sets of events happen And you are not knowing why it continues to come up heads. You think if it happens half the time heads, shouldn't it be happening half the time tails? Tails happens, again, the exact same probability of heads because it's one outcome of two possibilities. So again, each time I flip the coin, tails, 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 it should have the exact same probability of coming up heads and tails. What starts to freak you guys out is that it was coming up all heads and now it's coming up all tails. Why is that happening? Well, what we're not seeing is a random series of events. Because if we were, the probability that what you just saw happens is so low that we can pretend almost that it's impossible to happen. And obviously we can claim that what wasn't happening was a fair flip of a playing coin. A fair flip of a playing coin comes up half the time heads, and half the time comes up tails. So, when you see in a row a sequence of events that is going heads, 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 any one of those is not improbable. In fact, it happens half the time. But when you consecutively see that happening again and again and again, when half the time it should be coming up the opposite, this gives us pause and this makes us go, I think Professor Frazee is doing something strange to make it come up whatever he wants. All right, what do you want? What do you want? You ready? You want it to be heads or you want it to be tails? All right, I'll do one for you heads. Okay, so here's heads. And then do you want one tails for those of you who like tails? You want tails? Tails. All right. What's going on here? Well, it's not random events. Heads. Tails. I'm manipulating it, obviously. Otherwise, you wouldn't be able to call out what you want. We call out what we want when we flip a coin because it gives us randomness. Randomness of two known possible outcomes. We know how probable they are, and it's even, it's equal. So if there's two sides, both want something, we flip a coin to figure out who gets to go first, who gets to go second. We figure those things out in a football game, right? They start with a coin toss. And that determines, a random event determines who gets to go first in that type of a situation. So we like probability only if it's really random the way that we think it is. We want to understand that and we want to be able to identify when something's happening outside the normal set of events that we would expect in the future to predict uncertain outcomes. The same thing could be true for probability in terms of a die. A die is a six-sided piece, so it's got a 1 on one side, a 2, a 3, a 4, a 5, and a 6. So there's 6 possible outcomes now. The denominator in this calculation is 6. But I'm going to roll it, and only one of those is going to show up as the top one. Only one of those is going to land up. So that will be the one that we have in the numerator. What's the probability of it landing a 6? Is it more likely to land a 6 than a 5? Well, you could take how many 5s there are. There's 1 5. How many possible outcomes there are? 6. And there's 1 out of 6 possibilities that it comes up a 5 when I roll it. Now, if I was manipulating this and somehow figuring it out that I could make it go 5 all the time, you would be able to see that very quickly. Whereas it took you a little bit more time when there was only 2 outcomes with the coin. This I will roll fairly, and so we're going to see some randomness here. I roll this dice and I'll get a 4. That's a 6. A 2. A 4. A 1. A 1. A 4, a 1. How come we're not seeing any 5s? What's going on here? I thought there was 1 out of 5 things. A 1, a 5. You see, Gambler's fallacy says that 5 was due. It says that because we hadn't seen 5 and it's one of 6 possible outcomes, we should be seeing it more and more. The problem is our limited set of understanding that the probability of it coming up 5, it could come up 5 twice in a row, or it could come up 5 once every 10 times, and that was still sort of within the realm of possibility. Still haven't seen that 5. Oh, there it is again. If you are looking for an outcome, you might misrepresent how likely those outcomes are to occur because you're expecting it more often than it should come up with randomness. Whoops. I dropped it. That's a 1. All right. So, 1, 6, 6, 4, 6. I should have some sort of a box here. 5. Again, you've been looking for that 5 and we haven't seen it. But I haven't rolled this thing more than, say, 20 times. So in that sense, we're not really violating any probabilistic outcomes here. 3, 1, 5. Look at that. 5 again. 1, 5. Hey, it's starting to come up again. See, the gambler's fallacy is this idea that something's due. Oftentimes, you'll see roulette games played this way, where at a casino, they'll have a list of how many red and how many black outcomes have there been. So basically, half of a roulette wheel is red, half of it's black. Not exactly. There's 2 spaces that are green. And this throws off people's ability to understand the probability of outcomes. So we have to understand what's the outcome possibility in this scenario. Rolling a die is 1 out of 6. There's 6 possibilities. So if I said to you, what's the probability of it coming up a 5? It's 1 out of 6. If I said to you, what's the probability of it coming up a 1, a 2, or a 5? That would be 1 would be a 1 out of 6 plus 2 would be a 1 out of 6, plus 5 would be a 1 out of 6. So together that would be a 3 out of 6 probability statement. Because I said a 1 or a 2 or a 5, all of them have the same probability, but when I say or, we're going to add together their individual probabilities to come up with 1 out of 2, or 0.5. The probability of getting a 1, a 2, or a 5 on the fair roll of a die, it's a 1, oops, is the same as the probability of flipping a fair coin and getting a heads. So probability theory is a theory that's been developed through the help of some excellent mathematicians and has helped us to understand things, but it didn't start out to help us understand just psychological science. It helped first to solve the problem in gambling. There was a man by the name of Charles de Mer, and he was a gambler, and he was this French guy, and he had a buddy who was also a French guy named Blaise Pascal. You may have heard of Pascal before because Pascal's a famous mathematician. He asked Pascal to solve a problem for him, which was an interesting problem, which I think is a very interesting probability problem, and it was, what's the probability of rolling a die 4 times and getting a 6, or rolling 2 dice 24 times and finding that one of those outcomes was a double 6. This is an interesting problem because you can set up those probabilistic outcomes just like we've done before with these numerators and denominators of outcomes that would satisfy what we're looking for, and then all possible outcomes, and find a decimal that gives us a relative chance that we'll see that type of thing. Random experiments employ probability to help us understand what we would expect and what we would not expect. And this is the basis for hypothesis testing. It's simple to understand the probability of flipping a coin or rolling a dice, but as we get to more complex things like, say, human behavior, whether or not your particular study habits are going to result in the outcomes of the grades that you want for this class, we have to start bringing in more complexity. And so what if I bring in the complexity of a set of cards? So if you guys don't know about playing cards, I told you that Pascal did playing cards or gambling. And so cards is a way that we can do that. So there are 52 cards in a deck, and these are organized into suits. Okay, these are hearts, these are diamonds, these are clubs, and these are spades. Oh, there's a joker there, gotta get rid of him. No jokers in our deck. So, there's 52 cards here, which means all possible outcomes is gonna be 52. What's the probability of drawing any one individual card out of this deck? It's gonna be 1 out of 52. Pretty unlikely. But, what if I said, what's the probability of drawing a heart out of this deck of cards? When 1/4 of all the cards in this deck are hearts, then it's 1 out of 4. And so there's 13 cards that are hearts. Therefore, 13 divided by 52, or if we reduced it to 1 and 4, gives you a probability of 0.25. 0.25 says that basically, if you were to randomly sort through this deck of cards, if I shuffled them up, right? So, oops. I'll shuffle them here. I'm gonna shuffle them up, and then we'll see what's the probability of getting one of those hearts. If I shuffle them adequately such that there's randomness in this, then we should see a probability of 1 out of every 4 times we select a card, it's going to be a heart. Now, if it's done truly randomly, you'll see that evidence, but you're not going to see it happen right away. You might get 3 hearts in a row, but is that something that we would think of as so improbable that it means that he's doing something weird? Or is this true randomness? Was diamond? Oh, it was a heart. So 1 out of 2 cards. Oh, it was another heart. Oh, it wasn't a heart. Diamond. Club. 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 Diamond. 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 Diamond, diamond. What's going on with that? That means that I didn't shuffle it adequately. It was all organized and I didn't do enough shuffling to get it truly random because we started to see diamond after diamond after diamond. That pattern is so unlikely when I do that many in a row that suggests, hey, you gotta shuffle your cards a little bit more. All right. Okay, so here we are at Cosumnes River College Casino. We're gonna play a game of chance, okay? We'll play a Texas Hold'em. If you know how to play Texas Hold'em, basically the cards go, you get 2 cards, I get 2 cards, and then we'll get 3 cards in the middle that basically are the ones that we can play as a community, okay? So when we do this, trying to get them all random here. Okay. Now, you get 2 cards. Those are your cards. And then I'll get 2 cards. Okay. I burn a card. And then I put up 3 cards. So, what we're gonna try and do is build the best 5-card hand that you could have with your 2. I'll let you see yours. Okay? I won't let you see mine. And then we'll make a wager. I'll say, I'll bet you 1 homework assignment that you'll have to do double if you lose this hand. Or if I lose this hand, then you don't have to do the first homework assignment that I give you after this lecture, okay? So would you guys like to bet that? I'm guessing you would. If you don't, then turn this video off and don't learn any more about probability. Just kidding. So what now happens is we burn another card and another card gets put up. Ooh, so now we can use queen, jack, ace, and ace to make our hands better. Again, these are your cards. These are my cards. You can't see what they are because I'm playing. Otherwise you'd know if to bet with me or not. So I like that double ace. So I'm going to say, I'll bet you another homework. Does that sound like a fair game? Another homework? You and I are betting if you lose this hand, you have to do both this homework and the next homework. But if I lose this hand, then you don't have to do this homework or the next homework. Sound fair? Good. Then we get the last one. A 9. 9 of clubs, nine of spades, ace of spades, ace of diamonds, jack of clubs, queen of clubs. So, what do you want to do? Do you want to bet? I want to bet all homework this semester that I win. Do you think you could win? You've got those cards. And maybe you could win. I don't know. What do you think? You want to make that bet? First rule of Statistics Psychology Club. Never take a bet that a man brings to you. I've got 4 of a kind.
There's no skill.
Okay, so I brought my boys. I brought my boys in to play a game of chance. Now, there's 52 cards in this deck, so if each of them got half, that would be 26 cards each.
Yep.
And if they're playing a game of war, what they'll do is they will play a game where the highest card is an ace, the lowest card is a 2, and whoever has the highest card, that card wins and they take both cards. So we could calculate the probability that any one of these cards is the highest card in the deck, and if they tie, they then go through a round of putting 3 out and then playing another card against one another. You ready for some war, class? This is just a probability game, so here we go. Jonah, you get 26 cards. No, I don't think there's pizza dough. All right, 1, 2, 3,
Jonah, do not
4,
look at your cards.
5, 6, 7, 8, 9,
your card.
10, 11, 12, 13, 14, 15, 16,
Oh my god.
17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay, now these two guys are going to play war. Okay, what you're going to do is you're going to stack these cards up and you're going to take from the top. And you'll place your cards down right here, and whoever has the highest card will win. Go ahead, Jonah, put your first card down here. Put it down right there. He's got a 7. Henry's got an ace, so he wins. Okay, go ahead, play again.
I just take this one.
He's got an 8, he has a 3, he wins. Go, come on, keep going. 6 versus a 7, 7 wins. Queen, oh, that's a high card. Let's see what you got, Jonah.
I got nothing.
A 9, Henry wins.
Do you want to try and do it fast?
2 versus a 9, who wins?
I do.
Yep, okay. Here, take these and put these down right here. And then you can just keep playing.
I can do this.
Put it over there. All right, go ahead, keep playing.
Okay.
So, as they're playing, what we're seeing is that the probability that anyone, let him get his win. You get your own win. The probability of them winning is determined by how many cards have been played, which cards have been played, and which ones are available to be played. So because we have these unknowns here, this is a probability situation where as we gain more and more knowledge of what cards have been played, then through Bayesian logic, we can determine who's more likely to win the subsequent hands.
Who wins?
You do. You have a queen. Queens are bigger than jacks. Kings are bigger than threes. This guy's winning a lot. However, as these go down and down and down, the probability is going to shift in his favor if he has the higher cards. If he wins a high card versus a high card only slightly higher versus winning a high card versus a very low card, 3-2, that's not going to really help Henry's chances. This type of probability is done in casinos all the time. If you've ever watched World of Series poker, they'll have for you calculated probability that somebody will win a hand. And what they're doing is they're saying, we know what cards have been played, we know what cards are in their hand, so the possibility of what comes up on the next one, that is going to give us a sense of the probability that either person will win. Now, when you watch those shows, they tend to show not the thing that happens most often. And so you think that people get beat when they shouldn't get beat more often than they do because they're showing you outliers. That's what makes people excited about games of chance, is when something unexpected happened. If he won half the time and he won half the time, it wouldn't seem to be very interesting. But the story, the narrative that we develop, has to do with the gambler's fallacy, that something is going to change the laws of probability such that a different outcome will occur.
Who's winning so far?
Who do you think is winning?
Me?
You have most of the cards. Ooh, ace queen. He just took down a big one. Jack, 10. Can't believe that we haven't had ace 7. All right. Take that?
I,
Yep.
who,
8
who won?
versus 6. Okay, so now you flip these cards over and you start playing again. Keep going. You have many more cards than him. Uh-oh, a 2 versus an ace. A 9 versus a 4. Now, given that he has more cards, it doesn't necessarily mean he's going to win, because it has to do with the constitution of each of their decks. If he had all face cards, he would start winning more of those shares. This game of chance really allows for a lot more extended play. It's very, very irregular for one person to win in only a couple hands. They'll have to continue to play hand after hand after hand, where they go through their entire decks before one of them will get all the cards. And typically, if you have kids and you want them to be distracted by something, give them a random chance game that goes on and on and on. Just like war. Can't believe you guys haven't had a war yet.
Me neither.
Just battles. I can't wait for a king and a king, or an ace and an ace to come up.
And then another ace and an ace.
Jackpot.
I lost.
I could watch them all day.
Jackpot.
I lost again.
Keep going. Call out your cards.
Ace.
Queen.
7.
Wait, queens are stronger than aces.
No, aces is the strongest card.
Oh, king.
King's pretty strong.
6.
6.
10. 7. I got more cards. Queen.
I am.
8.
Ow.
Ace. I take whatever you have.
You guys want some juice?
Yes, please.
I haven't had
7.
this types of juice in years.
No, 7. I played 7.
All right, he's played a 7. His cards, what's the probability of him winning? Well, if all things were random, we could take a 7 and say, well, where does it stack up in the line of all 13 cards? Right, there's a 2, 3, 4, 5, 6, and 7. And then there's the 8, 9, 10, 11, or Jack, Queen, King, Ace. So his card if all things else were equal, would be most likely to lose this hand because it's on the lower end of probability.
Can you help me?
However, he won.
Put this in. It's really hard. Okay.
Yay. 8.
How are you?
Jack.
Can't do this.
I know.
There you go. Jack is on the higher end, so he's most likely to lose. Or win, I'm sorry. So Henry's is on the high end, most likely to win. Oh, it's a queen versus queen. So we put out 3 cards. 1, 2, 3, and we flip one
3,
card
2,
over.
1.
Ace versus 7.
Wait, are we on war?
Yeah, that was a war.
He won an ace, a queen, and a 3, and he would have lost a 3, a king, and a 7. Nice job, Jonah. All right, Jonah, I'm taking you to Vegas, buddy.
Las Vegas?
Lost wages.
Like the place we went to?
4 years later.
There.
Like 1,000 years later. Oh, please, no, please. You just won yourself a 5. I'm going to see what I have here. Oh my gosh, I'm beating you. Oh, please, no. No! Gosh, please, no! No!
So again, if we're dealing with a deck of cards and we wanted to determine the probability of a single card coming up, we would take the full set of possibilities. And so for those of you that don't know, I'm going to go through what they have. In each deck of cards, there's 4 suits. Of the 52 cards, then half of those 52 cards, are black, so 26 cards are black, and 26 cards are red. So, if you were thinking about what's the probability of a red card coming up or a black card coming up, it's just 0.5 because half of the cards are red, half the cards are black. So if we want to know about what's going to happen in the future, you can guess, and you'll be right, given the law of large numbers, that over time, half the cards will come up red, half the cards will come up black. Now, a further iteration of division is that each of these red and black cards have 2 suits, and these are different shapes associated with them. The first shapes are spades and clubs. These are the 2 black suits. And then the 2 red suits are diamonds and hearts. Each suit has 13 cards in it. So there are 13 hearts, 13 diamonds, 13 clubs, and 13 spades. The cards all include the same setup so that each suit has an ace, a king, a queen, a jack, 10 through 2 numbers. So the cards are 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, ace. That's true for each one of these. So there's an ace of spades, there's an ace of clubs, there's an ace of diamonds, and an ace of hearts. So if you wanted to know what's the probability, I don't know where I put my cards. Oh, the kids are still playing war. All right, kids are still playing war, so you don't get to see them. But each of these suits all have one of these. So if I said, what's the probability of the very next card of a fair deck of playing cards that's been shuffled so they're random, that you pull out an ace or a queen? You would take all the aces that there were and all the queens that there were, because those would satisfy events that are positive for... Well, that doesn't work. These would all be the numerator. So we would say, look, there are 1, 2, 3, 4 queens and 1, 2, 3, 4 aces. And because there are 4 queens, 4 aces, that's 8 total. So of the 52 cards available, 8 of them would be available. And so 8, if we took 8 as the numerator and the denominator is 52, 8 is the numerator, denominator is 52, that gives us a 0.15 chance, basically. So the probability that you're going to get an ace or a queen on a single card dealt from a fair deck of playing cards is about 15% of the time. Note that probabilities are spoken in terms of decimals, but you could sort of think of it like how often when I get a card is it going to be an ace or a queen. When you say ace or queen, that includes both the probability of an ace coming up, which is 4 out of 52, and the probability of a queen coming up, which is 4 out of 52. So together, 8 out of 52 is about 0.15. The probability is about 0.15. Now, if you already have an ace or you already have a queen, you're going to reduce that. And so you'd reduce the denominator, you'd reduce both the numerator and the denominator if you have cards out that you know are already there, because that wouldn't be the random set of things that could happen if you already have one in hand and you know what it is. You know that it's a queen or an ace. So in our situation when we were playing cards, if you had in your hand the 2 aces I had, you would take them out. I forget which ones I had. Let's say that there was 1 black one and 1 red one. And then in my mind, I'm going to change not only the numerator, going to 6 possible cards, but I'm going to change the denominator by 2 because I know about those 2. So that would be 6 divided by 50. So in that sense, 6 divided by 50 gives us 0.12. So there's a smaller chance now because 2 of those aces were in my hand when we were playing cards and I had both the aces. Then I didn't know what the probability of these other things coming up. I could do this type of an equation to figure out what's the probability of a queen or aces coming up. And that's how probability is used in gaming scenarios. Now, how is it used in testing scenarios, like for experiments in probability? That is we're going to have to go back to the normal curve after we hang out here in gambling land for a bit. We're going to have to go back to the normal curve and get into hypothesis testing, understanding that really what we're doing is calculating probabilities, p-values, for how often we'll see some rare event happening in our experiment. For example, when you saw me get 4 aces in our game that was clearly rigged, again, never take a bet that a man brings to you, and you guys have to do the homework now. In that sense, you're calculating the probability of that rare event happening where I get all these aces. You're thinking, I got a pretty good hand, I got 2 pair. But you're not thinking he's got this incredible hand because it happens so infrequently. What we're going to do in hypothesis testing is look for that rare event. Is this something that happens really infrequently? And if it is, we're going to be willing to say, those things were not the same. Now this is different from this other thing. That's where we're headed with probability, and we'll get into that as we do hypothesis testing. So back to stats. Hope you had fun in gambling land. I hope you enjoyed all these sort of probability stuff. Let's get our heads down and hunker in for some real good hypothesis testing. One more thing, and this is relevant a little bit for sort of psychology and playing games and whatnot. I showed you the addition rule, which is when we say, what's the probability of getting this and this? Or this, right? A queen or an ace. But what we need to consider is, what's the probability of getting a queen and an ace? If we do that, then we're going to have to multiply those independent probabilities together. So let's put it to you this way. I'll clear this board off and give you guys another example so that it's at least a little bit more clear. If I had my coin, right, here's that coin again. If you said, what's the probability of flipping a coin and getting a heads once, you know it's 0.5 because there's 2 things that could happen. One of them is it coming up a heads. But if you said, what's the probability of a coin being flipped and it coming up heads 1, 2, 3 times in a row? Remember when you were seeing all those heads? and then I switched it to tails. If we're really calculating the true probability of something, when are you going to start being curious as to whether or not that's a fair flip of a coin? On the first flip, if it's a heads or a tails, you have no sort of bearing on that. If it comes up heads twice in a row, then you start to go, huh, that's odd. But that still has, if you calculate the probability of it coming up a heads and a heads on 2 consecutive flips of a fair coin, it's not improbable. It's just like picking a diamond or a heart or a spade or a club. 0.25 probability. Let me show you how we calculate it. The probability of the first flip... Sorry about that. The probability I pick up a dry erase marker that actually works. The probability on the first flip is 1 divided by 2, so that's 0.5. You know that. But if we're not calculating the probability of it happening just once, but on subsequent iterations of this game, again, this second time I flip a coin, the same properties exist. There are still a head and a tail, and only a head would satisfy this second event. But this second event only gets to happen, if we're talking about heads and a heads, half the time, because half the time the first flip is a tail. So now what we want to know is, what's the probability of flipping a coin twice and it comes up heads, heads. Whoops, I dropped that one. Ah, it did come up heads. See? Can't see that. Sorry, my camera's not that great. It's heads. What's the probability of coming up heads and heads? Now we're going to use the multiplication rule. The multiplication rule says that we take each event's individual and mutually exclusive probability, and we're going to multiply it. Because I asked, what's the probability of flipping a coin once and getting a heads, and flipping it twice and getting a heads? And means that we use multiplication for the individual probabilities. So 0.5 times 0.5, or half of a half, is a quarter. See that? 2 times 2, 0.25. So the probability of flipping a coin twice and getting 2 heads is 0.25. That happens, if I sat here and just flipped coins a whole bunch for you, it's going to come up every fourth time that I flip it twice, it's going to end up being heads twice. I have a hard time looking at you and flipping coins. But if I do this and I just keep going, it happens very often that twice it's going to be heads. It's 0.25. Well, then we get into the difficulties of, when do you become skeptical of me flipping coins and it always comes up heads? When do you start to get curious as to whether or not I'm doing something that's not a fair flip of a coin? And that's a great question, because that says it's different from this probability distribution that we're understanding. This probability distribution suggests that I can figure out what's the likelihood, which is another way of talking about probabilities, is the chance or the likelihood. Now, if I have a coin and I say, you know, when I initially was flipping that coin for you, I flipped it, I don't know, 10 times? 10 times, I think I did. So how do you calculate the probability of flipping a fair coin and getting 10 heads in a row? You do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 events. You know that each of them has a 0.5 probability. So now what we're going to do is multiply every single one of these probabilities together. So we'll go 0.5 times 0.5, that's the second one, times 0.5 the third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. Not sure if you can see this, but here's what it says. It says that basically, 1 time in 1,000, 1 time in 1,000 times, not of flipping a coin once, but of flipping it 10 times, one time in 1,000 10 flips of a coin, do you get heads, 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 heads? So is that what you think happened? Clearly not. You guys know I was manipulating those tosses. I was doing little funny things to make it always comes up heads. That's the skepticism I want from you, is I want you to say, that's not right. That's not what we see happening, or what we think is happening is separate from what is happening, because it's so unlikely that I'm willing to be wrong. When you call out your professor for flipping a coin unfairly, you should do that. You should say, it can't always come up heads.